Hello everyone and welcome back to my channel. We were studying the concept of concurrency and synchronization, and in this video we are again going to look at few of the important topics of the very same subject. And these topics are important because they are frequently asked in various university examinations as well as in interview questions. So without wasting time, let us start with our first question. So what it says, what is the meaning of the term busy waiting? What other kind of waiting are there in operating system? Can busy waiting be avoided altogether? Explain your answer, right? So the answer is something like this. Busy waiting means that a process is waiting for a condition to be satisfied in a tight loop without relinquishing or giving up the processor. Alternatively, a process could wait by relinquishing the processor and block on a condition and wait to be awakened at some appropriate time in the future. Busy waiting can be avoided but incurs the overhead associated with putting a process to sleep and having to wake it up when appropriate program state is reached. So that was the theoretical explanation, and it can be a little bit overwhelming. So let us understand this particular question and the meaning of busy waiting with the help of an example, right? So now on your screen you can see a sort of a chart or a diagram which says that the synchronization mechanisms that we have in our operating system for smooth process execution can be of two types, right? So synchronization mechanism are of two type. The first one is with busy waiting, and of course the second one is without busy waiting. So this is going to answer the question that what we understand by busy waiting, and is there any other mechanism apart from busy waiting for synchronization, right? So this is going to completely explain the question number one which we have. So let us now study the synchronization mechanism with busy waiting first, right? So what happens in busy waiting? See, we have studied the concept of mutual exclusion and critical section in our previous videos. So here I will be asking you guys that if you haven't watched the previous videos, so first go to the previous videos of my playlist and just go through them once, so that you will be pretty much aware that what is mutual exclusion and critical section. So here I am assuming that you are well aware of mutual exclusion, race condition and critical section, right? So all these three terms are pretty much clear to you, right? Now suppose we have a multi-process environment. So I have two processes with me, that is process 1 and process 2, and right now process 1 is executing its critical section, right? So it is right now executing its critical section, and as per the principle of mutual exclusion, we know that only one process is allowed to execute its critical section and the other processes should wait, right? No two process can execute their critical section, right? Otherwise they will be giving rise to the race condition, and we have to completely avoid that particular situation, right? So P1 is in its critical section and the other process, which is process number P2, it is waiting, right? If we apply the synchronization mechanism with busy waiting, right, the consequence will be that this process number 2 will be constantly pinging the CPU, right, that if it is my turn to get into the critical section, right? It is waiting, but it is constantly being executed by the CPU, right? There it is executing its while loop, right? In while loop there may be certain condition which says that now it is the chance of process number P2 to get into the critical section, right? We have seen several constructs programmatically, like producer consumer problem or reader writer problem. So every process have its complete programmatic constructs in it, that is the entry section, which is the while loop, right? So it on constantly being executing its while loop, right? And it is do nothing, it is not doing anything, right? It is just constantly executing its while loop and it's doing nothing. Why? Because it is waiting that let P1 get out of its critical section, then I shall be entering in it, right? So it is constantly executing, but it is doing nothing. If a process is executing, that means it is keeping the CPU busy all the time, right? But it is not executing, it is doing nothing at that point of time, no fruitful task. It is keeping the CPU busy, right? The CPU is busy at this time, but it is not doing any fruitful task. That is why we have the term busy waiting, right? So, right, P2 is waiting, but it is keeping the CPU busy. So it is an overhead for the CPU because it increases the CPU utilization, but you do not perform any execution, or the process is not being evaluated, right? So that is what the term busy waiting actually means. Now coming to the synchronization mechanism, which is without this particular concept of busy waiting. Again, we will be having a critical section, right? In each of the process, P1 will also have its critical section, P2 will also have its critical section. And right now, P1 is executing in its critical section, right? So what happens, the other processes which are waiting to execute their critical section goes to sleep, right? So what we do in this particular mechanism, we put the waiting processes in the waiting queue, right? So they do not bother the CPU. What they do, they reside in the waiting queue, right? And they wait until they get an awakening call from the process which exits the critical section. So this will be residing in the waiting queue, and as soon as P1 get out of its critical section, it notifies P2, right? It will be notifying P2, right, that you can enter your critical section. So P2 will reside in its waiting queue until it gets a waking call from process P1, right? So this is a CPU friendly approach which we should follow, right? What we should do, busy waiting is an overhead, right? This is an overhead. This keeps CPU busy unnecessarily. So this is an overhead. We should not keep our CPU busy unnecessarily, because that will be putting down your throughput, that will be putting down your CPU utilization will increase, but it will not be doing any fruitful task, right? So the best thing is to do it with busy waiting. This is somewhat this particular concept of without busy waiting is programmatically overhead generating, right? So it will be generating overhead to the programmer, because we have to write code which will keep the waiting processes in the waiting queue. Then we have to write certain lines of code in each processes, that as soon as they exit their critical section, they should give a signal, or they should give a call to the waiting processes, so that they can come out of the waiting queue and execute their critical section. So this is bad for your CPU, right? And this is bad for the programmer, but programmers are meant to program, right? So we can actually go with without busy waiting concept, so that the CPU utilization, throughput and waiting time, everything should be in its ideal situation. So that was the explanation of question number 1 about busy waiting, and I hope that this concept is clear to you all. Now let us move to the second question, which is something like this. Show that if the wait operation and the signal operation on semaphores are not executed atomically, then mutual exclusion may be violated. So now what this question says, it is saying that we have, again, I hope that you know what is wait and signal operation. So what it says, that wait and signal operations are there in each process, right? Because we are writing it as per the critical section programming notation. So each of the process will have their wait operation and signal operations operating on the semaphores, so that they can access their critical sections, right? So it is saying that no two process should execute their wait operation or their signal operations simultaneously. They should be atomic, one process at a time. If it has not been done, then the property of mutual exclusion will be violated. So we have to prove it right now. So let us see what the answer says. Wait operation atomically decrements the value associated with the semaphore. Definitely it is a decrement operator. If two wait operations are executed on a semaphore when its value is 1, okay, if the two operations are not performed atomically, that is if they are performed together, then it is possible that both operations might proceed to decrement the semaphore value, therefore violating mutual exclusion. Right? Now let us again understand this with the help of an example. Right? So here let us say that the value of my semaphore is equal to 1. Right? We have process 1 with us and we have process 2 with us. Right? Now suppose that this process execute its wait operation. I am writing it in short, okay? So it apply this wait operation on this semaphore. So it changes the value, it decrements its value to 0. Right? It is fine, there is no issue. Right? This value 0 indicates the value of semaphore 0 indicates that right now there is a process which is executing its critical section. Right? So this is the value 0 indicating that someone is in its critical section. So this other process must wait. Right? So if this particular process is the wait operation is not atomic, that means at this point of time process number P2 will also execute this wait operation on this value. Right? It will again going to decrement it. So it will again going to decrement it and change its value to -1. Right? Decrease by 1. Right? So this becomes the issue. Now meanwhile the process is executing and this process is also executing. Right? Now this process after exiting its critical section should signal the value of semaphore. Right? So it should now, this was the decrement operation and this is the increment operation. Right? So it should now increment the value of semaphore. So after incrementing this value, the value becomes 0. Right? And again this process is in dilemma because 0 indicates that the process should wait. So this is a problem over here because the second process is not able to decide whether I should go into the critical section or not, but this process has exited the critical section. Critical section is free at this particular time, but this process is in dilemma. So there is an issue that when to enter the critical section or when should not, because programmatically we have designed it to work in this particular manner. So now let us understand that yes, the value of S will be 1 in the beginning. What happens if the wait, this is by process P1, so it sets its value 0 as I told you, and this wait operation by the process number P2 sets its value to -1. That is also I have explained you right here. So this will have certain complications. What complications it will have? That because of this particular value, this -1 value, it will not allow the signal, right? Because the signal, even after performing this signal operation, the value is 0. And if the value of semaphore is 0, then we have a waiting queue over here which will be having process number P2 waiting while P1 is in its critical section, right? Because this value is 0, this process will not get out of its waiting queue. This will get out from the waiting queue only when the value of semaphore is 1. But we do not reach this value because these operations were not performed atomically, they were performed together. The value becomes 0 and 0 doesn't allow a process to move out from this waiting queue. Only the value 1 allows the process to come out of this waiting queue. So that is the issue. Process will not actually enter in its critical section even if there is no process executing the critical section. So that is the problem. So wait operation, both the processes, that is both process number P1 and process number P2 should execute their wait operations atomically. That is, only one process is allowed at a time. Similarly, if two same signal operations increments the value. See, if signal operations are also performed atomically, if they are not, then they will allow two processes to get into the critical section, which is of course not desirable, because we are working upon the principle of mutual exclusion, because we do not want race condition to arise. So here with this particular illustration, we actually conclude that we should operate any operation. Two operations are allowed on a semaphore. One is the wait and the signal, and these two operations should always be in order. That is, first wait, then signal, right? Each process should follow this particular ordering, and no two process should execute the wait or the signal operations together. They should be atomic, right? So that was our explanation for question number 2. I hope that this explanation is clear to you all, and I think that will be all with this particular video. Yes, and I hope that this topic is clear to you, and if there is any questions or any queries, feel free to ask in comments. And thank you so much for watching, and I will be seeing you in the next video.